Episode 5, digit sum. Let's recap the problem statement. We introduced a function of two parameters b and n, sum of digits of number n when it's written in base b. We are given n and s, and we want to find the smallest b such that f of bn is s. So the smallest such base such that the sum of digits of n written in base b is s. N and s are both up to 10 to the 11th power. And on the left you can see some example. If n is 27 and the sum we want to get is 3, we look at some different values of b, and 2, 3, and 4 are not good for us, but b equal to 5 actually have sum of digits equal to 3, so that's good. And in the lower part you can see some other values of b that would produce the correct sum, but we are interested in the smallest value of b. What would be the stupid solution? We can iterate over b, calculate the sum of digits, and check if it is equal to s. How to calculate sum of digits? Well, we have to convert n into base b and calculate the sum of digits. So what does it mean to write the number in base b? Well, we should find such digits di such that n is equal to sum of di multiplied by b to the power of I, and all di's should be non-negative, integer, and strictly smaller than b. From this representation as a sum, we can see that when we look at d0, it's just d0, and all other summands have b in at least first power, so all of them are divisible by b. So we can write our n as something multiplied by b plus d0. And we know that d0 should be non-negative and strictly smaller than b. There is a unique such value, and it is equal to n mod b. And this formula is just how we divide n by b with remainder. So this thing is n mod b, and this thing is n divided by b rounded down, and then we can recursively convert it to base b. So here you can see the kind of code of a function that would calculate the sum of digits. It's not C++, it's not like any particular language, just some code that is similar to C++ in structure. So we introduce a variable for the sum, and while our number is greater than 0, we increase the sum by the smallest digit and then calculate like this value and apply the same function to it. We could make it like recursive, but this as a while cycle is also fine. So that function works in time proportional to the length of the number in base b, but what is it in terms of b and n? Well, k, the highest non-zero position, should be the maximum number such that b to the power of k is at most n. But by definition then we can say that k is logarithm of n base b rounded down. Well, in programming we just usually say that log is log in terms of complexity. We do not specify the base. That's because all logarithms with constant bases are the same in terms of complexity. That's because of this formula. And here, instead of natural logarithm, you can put logarithm with any base. So if b is constant, then this thing is also constant, and so all the logarithms are equal up to a constant factor. But here b is not constant, so we need to actually write it. So the complexity is of this or of this. That's the same. Okay, that's the stupid solution. We cannot iterate over all numbers up to 10 to the 11th power, but 10 to the 11th power looks like we want to apply some squared heuristic. And yeah, we can just check all bases that are up to square root of n, and that will be square root of n log n. Well, this thing is at most log n by complexity. So how can we use that b is big to construct an algorithm that will solve this case? Well, if b is greater than square root of n, it means that b square is greater than n, so the length of our number is at most 2, or like k is at most 1. So we have only two options, k is 0 and k is 1. K is 0 just means that our number has length 1 in digit, so the only digit should be just equal to n, and also b should be greater than n. So if s is equal to n, just b should be greater than n, and that's it. So the answer is just n plus 1. Now there's an interesting case when k is equal to 1, so we have two digits and b should be between square root of n not inclusive and n inclusive. So n will be d1 times b plus d0, but also we know the sum of digits should be equal to s, but it is d0 plus d1. So if we fix one of the digits, we will be able to calculate the other one, but because we know their sum. And since b is greater than square root of n, to have d1 times b at most n, we have to have d1 smaller than square root of n, so there are only of square root of n different values for d1. If we fix d1, we can calculate d0 and then find the value of b, like this. And we should check that b is an integer, and don't forget about that, both digits that we use should be strictly smaller than b. I don't think that it should be an issue for d1, because like d1 is smaller than square root of n, and b should be bigger than square root of n, and I think that it should happen automatically, but I'm not exactly sure. So just check both digits that they're smaller than b, just in case. Okay, it seems that we solved the problem. That was easy, right? and the complexity of our solution is O of square root of n times log n. That's a true statement, but the complexity of our solution is also O of square root of n without logarithm. Why did we say that it's square root of n times log? The second half just works in square root of n time. But the first part, we are checking all the b's up to square root of n, and checking one b takes log n time, right? Well, not exactly. We said that it would be log n if b was constant, but b is not constant. So it's actually log n base b, or like O of log n divided by log b. And their sum is actually just linear in number of summands. Well, not always, but if the number of summands is a polynomial in n, there exists a power c that is strictly greater than 0, that the number of summands is at least n to the power of c, then the sum will be linear in number of summands. Why is that? Well, because for most of the summands, for example, if we say that we look separately at summands with b greater than fourth root of n, we know that the length of the number will be at most 4, or like in terms of logarithms, log n base b is strictly smaller than 4. So we will say that first fourth root of n summands, okay, let's just say that they are bounded by log n, but all the other summands, which are most of them, they're actually bound by 4, which is constant. So we can say that this sum is of fourth root of n times log, and this sum is of square root of n. So in total it works in O of square root of n. Alright, now we have a solution that works in O of square root of n, and n is up to 10 to the 11th. That must be it. That must be the intended solution. Surely we cannot do better. And well, the solution from the editorial is exactly this. And they don't even mention, unlike some other problems, that you can do better. But yeah, you can. A bit better. But it is smart, I think, and it worth mentioning. So let's try to analyze our problem more. So let's say that we fixed b, then n can be represented like this in base b, and s should be equal to sum of di. So what will happen if we subtract s from n? So n minus s will be the sum for I from 0 to k of di times b to the power of I minus di, or like di times b to the power of I minus 1. What can we say about b to the power of I minus 1? Well, you might know this formula, but you usually use it in the right to left direction. So this is a partial sum of geometric progression, and it can be calculated as b to the power of t minus 1 divided by b minus 1. But we can also use it in the other direction. Like, this equality is true independent of how you look at it. Well, except for b equal to 1, because don't multiply. Don't divide by 0 unless you really have to. So we can use it to say something about b to the power of t minus 1. For example, we can say that this thing is integer if b is integer, right? So b to the power of t minus 1 is divisible by b minus 1. So our n minus s is a sum of something where each summand is divisible by b minus 1. But then all of it is divisible by b minus 1, right? We can actually like write it like that. And it may provide some other insights. Like we can swap the order of summation here, maybe that will produce something interesting. But just the fact that n minus s is b minus 1 multiplied by some integer is already good enough to get a better solution. Because we can say that, well, okay, let's look at n minus s. It should be divisible by b minus 1. But then we can factorize n minus s, so find all the factors. And the only possible candidates for b are divisors of n minus s plus 1, because b minus 1 should divide n minus s. You should like handle s equal to n and s greater than n separately, but you probably should do that anyways. So we should only check divisors of n minus s plus 1. And we can check each of them just in stupid way in log n divided by log b. And like similar to what we have done to show that it is actually of square root of n and not square root of n times log n, we can show that the factorization is the slowest part. This problem can be solved just by factorizing n minus s, and it doesn't look like a big improvement. Like it's still square root of n, kind of, if like you don't have pre-written code maybe. But actually, like there are algorithms that do factorization faster than of n square root. Yeah, and you can Google them. Like this is some list of things you can try. Like Pollard's law is not very hard, and I think that SCUFOF stands for square form factorization, is also not that hard. Like it can be written in context. I think it's like less than 100 lines, probably even 50 lines maybe, and it is very fast. And yeah, there are like scientific algorithms that are amazingly fast. They're still not polynomial in lengths of n, but they're amazingly fast. Like they can factorize numbers of lengths, I don't know, like 100 in reasonable time. But they're not suitable for competitive programming for many reasons. But yeah, they exist. And I think that the last one I wrote here, general number field sieve, is the fastest known factorization algorithm. Yeah, that's it. Oh yeah, I wanted to say about this thing. So basically what we have used here is that n minus s is divisible by b minus 1, or to say it in different terms, and s are equal modulo b minus 1. So the number is equal to sum of its digits in base b modulo b minus 1. If you substitute b by 10, this says n is equal to sum of its digits in base 10 modulo 9. So to calculate the remainder of n modulo 9, you should calculate the remainder of sum of its divisors modulo 9. And you probably know it, at least as the property to check that n is divisible by 9. But yeah, it works exactly because 9 is 10 minus 1, and it works for 3 because 3 is a divisor of 9, so everything that works for 9 works for 3 too. Yeah, but it works for any base. In any base, n modulo b minus 1 is the same as sum of digits of n in base b modulo b minus 1. That's it for episode 5. Thanks for watching.